Without evaluation, science is limited to blind exploration. And even though reward models and automatic metrics get better every year, human evaluation remains the gold standard in deciding what is the best model to use. When I ran human evaluation a few times, I noticed that evaluating some samples did not impact the final model ranking, and we were just wasting resources on human annotating examples that were not useful. Today, we'll investigate how to make the evaluation more efficient and economical based on our TACL paper. Before we get to that, we need to establish the general setup. We have some inputs, some benchmark items. They go to all the models, which produce outputs. Then those outputs are evaluated, and finally we find out what the model ranking is. However, if we don't have the compute or annotation budget for the whole benchmark, depending on which subset we take, we might arrive at a different model ranking. Our task is to find a priori such a subset that would lead to the same ranking as if we used all inputs. Just as a ballpark figure, the cost of even a mid-sized model evaluation can easily reach tens of thousands. Let's formalize the task. We have a set of sources X, some models M, and we wish to find a good subset. Of course, you can take a random subset, which is what the majority of practitioners would do. That is surprisingly a strong baseline, but we can do better. Now let's put it together. We also have a cost function, which limits the size or some other cost of the subset, and we wish to maximize some utility of the subset. We'll define this utility for evaluation later. Optimizing this directly would be tricky, so we need to make a few assumptions. The first one is that the cost of a subset is the sum of costs of items. This is a benign assumption. Usually the cost is annotation or compute time, which is pretty additive. The second assumption is that the utility of a subset is the sum of utilities. This is a heavy assumption that might not be always true. It essentially says that the contribution of each evaluation item is independent of each other. Now we succeeded in turning this setup into an optimization problem. For a special case, where the evaluation of each item costs the same, we can simply take the top items with the highest utility until we reach the budget. And that is our solution. We'll revisit the more general case later. Shortly, we'll try different utility functions, and we want to know how well they serve for selecting the best subset. Out of many options, we choose two ways for assessing the subset quality. The first is a simple correlation between the ranking of models on the whole evaluation set, that is if we had an infinite budget, and the model ranking on the subset. The second corresponds to statistical power of the evaluation on the subset. In both cases, higher is better. We are finally getting to the results, which are illustrated on a case study on WT23 model evaluation. Across multiple languages, about 15 models were human evaluated for machine translation, which is obviously a very expensive undertaking. Let's see if we could have made it cheaper by being smart about what to human evaluate. For now, we assume that the evaluation cost of each item is the same. The first instantiation of the utility function is a random number generator, which leads to a random subset selection of a particular size. As expected, the larger the subset size, x-axis, the better the correlation, and also the higher the statistical power on the y-axis. Now we are finally getting to more informing heuristics. If we have an automatic metric that somehow approximates human judgment, such as LLM as a judge or quality estimation, we can use it in the selection. Specifically, we can prioritize evaluation items where models likely do not perform well. While this sounds natural, there is a reason why this doesn't work very well. If you select items where all models perform badly, it doesn't tell you much about which model is the best. So for the rank correlation, we don't do much better than random. This heuristic helps with the statistical power, but that's likely because it selects homogeneous subsets, so model comparisons have lower p-value. A much better heuristic is to select items where model outputs receive very different automatic metric scores, which is computed with the variance. The high variance might be the result of accidental noise, but also these items affect the final model ranking the most, because the ranking is based on averages across all items. So far, we have relied on automatic metrics, which in our case of machine translation was metric X. However, for other NLP tasks, we might not have such reference-less evaluation metrics, or running them might be too expensive, such as with LLM as a judge. An alternative to using the metric variance is to select evaluation items where models have varying outputs. This can be computed with pairwise similarity of the outputs either based on embeddings, card level F-score, or blah. Then we take the items with the lowest average pairwise similarity, which works quite reliably and doesn't require an automatic metric. Another advantage of this approach is that we'll avoid evaluating two similar outputs. Obviously, our work is not the first to tackle this problem, and there exist some prior methods. Surprisingly, they are inspired by the 1980s research on psychometrics, where the goal was to create efficient tests for students. Most of this research, such as on item response theory, is centered around multiple choice questions though, and in our paper you can read about how to extend this to evaluation items where the output is a text or some other modality. At this point you might argue that all of this is not worth it for the minuscule gains. However, if you have a limited budget, we need to do some subsetting. We can compute how much budget we would need to match what random selection would produce. Depending on what we care about, we can almost halve the evaluation budget, which is a massive saving. So far, we assume the constant evaluation cost of each item. However, in practice, that is not true, and it may actually cause troubles. For example, the utility might be correlated with the cost, so while we might be selecting more useful examples, we might also be selecting more expensive ones, which beats the purpose. For example, more difficult items also tend to have more mistakes, which increases the annotation time and the cost, which beats the purpose of the informed selection. Our problem turns out to be a well-known one, a 0-1 knapsack problem. Famously, this is an NP problem, but we can find a good enough solution with approximate integer linear programming optimizers. So far, we assume that we know the set of models M at the beginning, and we also have their outputs. In practice, that might not always be viable if the original set X is so massive that getting all outputs from all models is computationally too expensive, or if we are creating a benchmark that we don't know which models it's going to be used on. To this end, we also consider a setup where we just have the inputs, and we want to select the most informative ones. At first, this looks impossible, because for all our utilities, we need the model outputs, like for metric variance. We offer two solutions. The first one is to create an estimator of the utility, which we call pre-commit. This requires that we have some past evaluation data for the particle NLG task. The second solution is to pretend that we have some set of models M' that is somehow similar to M. Then we can get the model outputs from M' and compute the utilities as usual. This is known as artificial crowd. Both of these approaches work quite well, though understandably less than the output-based selection. Everything that we just talked about is wrapped in a Python package that's well documented and easy to use, called subset to evaluate. Though most methods are easy enough for you to implement on your own. In addition, the paper covers domain balance selection, selection on document level, potential biases, and a second case study on summarization. Let me conclude with a very opinionated but concrete list of recommendations for evaluation subset selection. If you have a good automatic metric, use metric consistency or metric variance. If you don't have a good automatic metric, use output diversity. If you don't have model outputs yet, use either the distilled utility estimator or an artificial crowd. Thanks for watching.